There is no heating in the coils or anything. So, yeah.
Primary and secondary connected? Or
They're not, it's just wires wrapped on top of each other.
so how do you transfer power from secondary to primary?
That's it. By Faraday's law. Yeah. So the primary will have the coils, right? Will have a current running in it, right? Why? Because, well, it's connected to the wall, let's say. We'll have a current running in it. And if there is a current running in it, and there are coils, there is a magnetic field, right? There is a magnetic field. Do we agree with that? Okay. There is a magnetic field. And if there is a magnetic field, there will be flux. So the flux through one of the loops, the flux in one loop, in the primary, the flux through one loop of the primary, here is the first assumption, should equal to the flux in one loop in the secondary. Okay? So that is that. So now let's apply Faraday's law to the primary and then Faraday's law to the secondary and see what happens. In the primary, Faraday's law says the voltage or the EMF in the primary, right, should equal to minus the derivative of the flux in the primary, right, dt. But is it the flux through one loop or the total flux? Faraday's law. Total flux, so I need to multiply by the number of loops in the primary. Okay. Maybe this one should say 1 P primary. 1 P. Okay. Now the voltage in the secondary, because the secondary coils are on top of it, they also have flux through them. And the voltage in the secondary should equal to minus the number of loops in the secondary times the time derivative of the flux through one of the loops in the secondary dt. Okay? So you probably can see what I'm going to do. I'm going to divide these two equations by each other, because if the flux in if both of these quantities are equal at all times, then their derivatives will also be equal at all times. And so these will cancel when you divide them. The minus signs will also go away. So you got the voltage in the primary should equal to the voltage in the secondary. I'm sorry, voltage in the primary by the voltage in the secondary will equal to the number of turns in the primary over the number of turns in the secondary. So you can solve for the voltage in the secondary by this. So the voltage in the secondary will equal to cross multiply, so you have the number of turns in the secondary over the number of turns in the primary times the voltage in the primary. Okay. Let's think about this a little bit. Let's try to think about what this relationship is telling us. It says the voltage in this secondary source that's connected to nothing. It's just, this voltage is just because it's induced, because of Faraday's law, is equal to the voltage in the primary times the ratio of the number of coils in the secondary over the primary. So for example, let's say the secondary has twice the number of turns as the primary. So N in the secondary is twice this one. So what do you conclude about the voltage in the secondary? It will be twice, right? Because NS over NP is twice. So if the voltage from the wall is 110 and you want 220, well, make your secondary coil have twice the number of coils as the primary coil, so you get 220. If you want 330 or you want 1,000, just make the ratio accordingly. That's called a step up, a step up transformer, because it's taking a lower voltage, and making it greater. And you can have a step down also transformer by making, let's say, half. This one is half, you get half as much. Okay.
So what's the point of having transformer?
Well,
why do you have that?
Why do you have a transformer? Well, not, first of all,
When do you use it?
we use it all the time, right? For example, our cell phone will not take 110,
right,
it will
yeah.
take the lower, yeah. So, how about the current?
Yeah.
How about the current? How do I get the current? Let's say, for the current, I will use the fact that the power given by the primary should equal to the power consumed by the secondary. And the power, remember, power in the primary should equal to the power consumed by the secondary. And power is IV. So the current in the primary times the voltage in the primary should equal to the current in the secondary times the voltage in the secondary. And this means the current in the secondary divided by the current in the primary will equal to the voltage in the primary divided by the voltage in the secondary. So it's a trade-off. You have higher potential, but you have lower current. Or you can have a higher current and lower potential. That's all I wanted to say about transformers. I didn't emphasize them, so probably. Yeah,
So the loops aren't touching, right?
they can touch.
Between the primary and secondary?
Yeah, I mean, they're insulated.
Again, oh.
Yeah, otherwise you'll have a short circuit, yeah,
That's
yeah,
right.
yeah. Yeah,
So for the two fluxes to be equal, they don't need to be the same area, or do the loops need to be the same area?
yeah, you would need to have them, you need to have your secondary right on top of your primary to ensure that the flux that goes through the primary goes also through the secondary, right?
So we presume that the current would produce a constant magnetic field.
Constant, no, it's not constant, the magnetic field.
How do you make the flux constantly magnetic
We
field?
don't want it constant, right? If it's constant, then you have no change in flux.
Oh, right, that's flux.
You get nothing. Yeah, if the magnetic field, the whole reason you have your secondary induced voltage is because of the change in the flux.
Right, but they should have the same area.
They should have the same area, yeah, your secondary should be on top of the primary. Yeah, if it's within it, if somehow you get your secondary somehow here, and your primary this way, you're not going to capture all the flux.
Right, okay.
So,
We are controlling number of turns of coils to try to make magnetic field the same, right?
the magnetic field is,
The magnetic field is not the same, but you're trying to make it the same.
I'm trying to change, make the flux the same.
Is it making the flux the same because it's making the magnetic field the same?
Yeah, oh yeah, so you're saying the magnetic field created by the primary
And
is
secondary,
the same magnetic field that passes through the secondary, yes,
yeah.
yeah, that's correct. Yes. But it has to be changed. Has to change. If it's direct current, if the magnetic field is constant, then you're going to have a constant flux, and then you will not have an induced field. This right-hand side will be zero. So, that was that. Let's see if I can do a 5-minute thing on AC circuits. Yeah? Okay, let's use an AC voltage. We'll start with the resistor. The book avoids complex numbers, and they do it algebraically. I mean, complex numbers are also algebraic. They avoid them, they do it geometrically, I should say. They use a geometric approach. I think it's a good approach. I'm going to use that. In the worksheet, we'll do complex numbers. So, again, on Thursday, my plan is to do the homework associated with chapter 30 as I covered chapter 30. So that you don't have homework for chapter, I'm sorry, 32, I should say, okay, 32. Yeah.
So we still going over chapter 31?
We will go back to it on Tuesday, yes.
Okay.
Yeah. So, AC circuits. So you would have your,
So we're gonna,
huh?
so we're gonna go back to 31.
We'll go back to
This is
31.
32.
Yeah, see, 32 is directly associated with 30.
Yeah.
I'm not sure why, it's usually every other book they do it that way, so that's what I'm going to do it. Okay. So you got your AC voltage, and the voltage is usually equal to some V0 times the cosine of omega times t. It oscillates with time. It's not direct, it's not constant. The voltage is not constant, it's AC source. Then you connect, that's the voltage. And then you connect to it, I think this omega here is how many times it flips per second, right? Radians per second. So the frequency of how many times this oscillates per second depends. I think they say in North and South America, the frequency is usually about 60 times per second, 60 hertz. And I think the rest of the world is like 50 or something. So it's near, about 50 or 60. So you have your resistor here, right? And so the first thing, what is the current? What's the current? Well, it's pretty simple. You got V equal to IR. That's it. V equals to IR. So the voltage is V0 times the cosine of omega times t. And that's equal to the current times resistance. And so simply the current is just V0 over R times the cosine of omega times t. That's all. So the current will change over time. Next one is the capacitor. Right? So the other question is what happens if you put a capacitor with this? So you can hook a capacitor, and later you can connect obviously an inductor, and then an inductor and capacitor, inductor and capacitor and resistor, or any combination you like. Oh, not a resistor, a capacitor. Right? So what do we say? Well, V, the voltage across the capacitor will equal to the charge on the capacitor divided by C, right? Q over C. So you got V cosine of omega times T is equal to Q, or I guess I can use the letter little. Let's use capital Q, why not? Q over C, right? I want to know the current. I would like to know what the current is. Well, I have to take the derivative of both sides, right, to get dq dt, and that will give me the current. So you got V0 minus V0 times omega times the sine of omega t is equal to 1 over C times dq dt, which is the current, right? This is the current. So we get that the current as a function of time would be minus omega c v0 sine of omega times t. But minus sine of omega t is the same as cosine omega t plus pi over 2. Right? So this is the same as pi equals to minus omega c v0, no minus cosine of omega t plus pi over 2. You can just transform the sine into a cosine. So now this is V, basically the potential, but it's shifted. And this is the current. And we usually have V equal to IR. So if you divide both sides by omega c, you get V equals to I over omega c. So 1 over omega c is playing the role of some resistance, some kind of a resistance. And it's called the capacitive reactance. And we'll continue with that. So next time we'll continue with this. So the plan for Thursday, we are going to go over chapter 32, kind of the highlights, and we will do the homework for chapter 32 in class. Yeah.
So, can you explain again why you did what it was asked cosine?
Yes, so I wanted to get some form of, I know V equal to IR, right? V equal to IR. So I wanna know what plays the role of resistance when I have a capacitor. And so by transforming the sine into a cosine, so this looks like the V. With complex numbers, it would be better. It would be more clear. So, that's that. So Thursday.
No meaning.